Okay, let's get started. So if you haven't picked up your homework 4 solution, your graded homework 4s, they're up at the front. So I just want to go through the solution, which is pretty straightforward, but I saw something interesting that it might be a really good project idea, because I didn't even think about it until I actually implemented this myself. So this method was about the method which is picking one random row at a time, and you just keep picking a row completely at random until you get one that's at least as good as the average. So what I did was, if I can learn how to spell straightforward, that might be good too. So what did I do? So I just made a little helper function right here that just says, does this row that I pass in cover this interaction? So if it doesn't, it returns false. If it does, it returns true. So what I do in the run function is I provide the TKV, and out pops the covering array that it makes at the end. So what I do is I make a bunch of interactions. I make all the interactions that could appear, and then as we go through, as we start covering them, I'm going to remove them from the list. So when the list has nothing left in it, then we're done because we don't have any interactions left to cover. So remember that the expectation of what we can cover is the number of interactions that are left divided by, multiplied by the probability that it's being covered. So for each one, it has a probability of being covered 1 over v to the t of the time. And so on average, we should expect that the number of interactions on average that we cover is the number that are left divided by v to the t. And take the ceiling, because the number that we cover is always an integer, and we know that we can get at least the average. So what I do in this while true loop down here is I just make a completely random row, no thought into it. Then I go through the interactions that I have and just calculate the number that are covered by that row using that helper function at the top. And if the number that we cover is at least the expectation, we're done. So we have the row that we want, or a row that we want. So that's why I break right here. And then by breaking, I append the row to the covering array. We add it on. And then I update the list of interactions to be all of the interactions that are not covered by this new row. So the ones that are still left uncovered. And that's actually it. Other than this bit down here, which is, here's a particular parameter, how many times I want to run each one, and then I just print how big the covering array is. So what I just implemented this at 3 a.m. this morning, and it took like 10 minutes to run these examples. So it's actually pretty... So I don't actually sort them here. You can sort them if you want by putting them into a list or whatever. But these are just the results that I got. And you can actually see that the results are pretty far from optimal. So even in the t equals 2 case, we're at pretty much twice as big as what the optimal answer is, because we know what the optimal answer is. And for the other ones, it's just as bad. So that's fine for this. But one thing, but any questions on the solution, the code that I have? Okay. So what I thought was, well, what we have here is that we're getting a row that's at least the expectation. Well, why don't we just shoot for the moon? Why don't we just try as good as we possibly can? So instead, but not trying to generate every single possible row in the process. Trying to make this more adaptive by trying to make the row as good as possible without spending too much time. So there's kind of a trade-off in trying to search for as good as you possibly can versus how much time it takes to do it. So this is what I did. So let's just repeatedly generate a row until we get at least the expectation. And then at that point, restart the search with the requirement that we need to cover one more than what that row had. So let's just say that the expectation is, let's just say 50, and then the num that we cover in this row is 75, for example. So the number that we cover in this row is at least the expectation, which means we'll add the row in the old code. But what we'll do here is we'll set the expectation. So it's not really an expectation anymore, so I'm going to put it in quotes, to be 76. So I know that I can get at least 75 because I found a row that does it. But I'm trying to figure out whether I can do even better than that. So I'm trying to be as adaptive as possible, trying to get as high as I possibly can without having to search for every row. And after a certain point, if I just search a number of times and I never find a row, then I just stop searching. So I artificially set it at 100. So after 100 tries, if I don't get a better result than, say, 76, then I just stick with the best one I've ever found. And that's basically the whole method. So it's actually much slower than the original code, but it actually gets much better results. Because remember, for the t equals 2 example, the optimal answer was 8. We can get multiple answers with 11 rows. So it's substantially better. I haven't tried this with the t equal 3 or t equal 4 case because that'll take a lot of time, but it's something worth thinking about and maybe to do for a project, because I don't think anyone's ever done this type of work yet. Basically, we're just trying to hill climb, trying to get as good as we possibly can at this particular point, and then once it becomes too hard to move forward, then we add the row and then resume the search from there. So that might be worth something to do. Any questions about homework 4 solutions? Anything? Okay, so there's one more homework, which is due on Friday, and then no more homeworks, thank goodness. Any questions on homework 5? Yeah.
I read through the slide description for ATeach, and one thing I wasn't sure about, I guess like in practice, was kind of what ATeach does, which is forcing the first T things of a row to be an uncoded interaction. I didn't understand how that would be put into like practice.
Yeah. So it always, so the idea is that we'll never add a row that doesn't do any good for us. So we'll always add a row that does at least something. So for example, so if we have an interaction, call it T, and let's just say that the columns are, need to turn off notifications. Let's just say 0 and 2, and then values, let's just say 0, 1, just as an example. Then let's just say in row R right here, let's just say that we have 5 columns, just as an example. Then in columns 0 and 2 here, if this is the one that we pick, this interaction is the one we pick, then we're going to force these 2 entries to be 0 and 1. So the interaction, we're forcing it into the row first before we touch any of the other entries. And then, although the ATeach method doesn't actually say, then we process all of the other columns in some order. Let's just say from left to right, but it doesn't really matter. So then we process that column, then we do the analysis that ATeach does based off that column and these fixed entries. So we fix T entries where T is 2 here. So we fix 2, and then we work with the other entries as the algorithm says to do. So a way to do this, like in terms of an implementation, would be to set, let's just say, all of the other entries to be like -1s. So you set every entry to -1, and then for a particular interaction, you can pick any one that you want that is still uncovered. Then you force it to be covered in this row. So it always will cover something that you don't have covered right now.
And so it doesn't matter how you write the values for the negative ones, how you swap them out with actual symbols.
No, it doesn't matter because the method says that as you just process them in some order. It doesn't actually matter. But in practice, it really does matter for like research in terms of what is the best strategy for which ones to do, but I don't actually care as long as you process them in some order. From left to right, right to left, random, I don't care.
So whatever order you do them in, our covering array would have these values.
What was there?
Whatever order we do assign the uncovered interactions in until we basically cover everything, we're still allowed to have unfixed values.
Yeah, that could happen. So like if every single uncovered interaction left doesn't involve that last column, then that one can just remain unfixed. So like if every interaction I have left to cover doesn't touch that column at all, then I can set that column anything I want. So you can just leave it as -1 or something.
So you basically when you generate or you force an uncovered interaction, some uncovered interaction to be there, and then you see if you can force other uncovered interactions to be there.
Yeah. So you just evaluate what is the best symbol to place in a particular position, depending on all of the other previously fixed ones. So like say for that second column, then you evaluate any interactions that involve that second column and any other fixed one, which would be the first and the third one in this case. So are there any interactions that involve the first two columns or second and the third? And you just evaluate what is the best symbol to place there. So that's basically the method. Any other questions on homework 5? Okay. Another thing I should mention is that we have 2 papers to read this week. So it's not 1 paper, it's 2 papers. So are the Wednesday people ready to present? So only one of them's here. So any questions about that before you present? Okay. The Friday people ready? Are they here? Okay, cool. So and make sure to talk to each other. Okay, so let's talk about post-optimization, probably the coolest title of any algorithm ever. So I actually gave a talk about something related to this called optimizing post-optimization, which honestly is the coolest title of all time, no bias whatsoever, right? So what is this idea? So this algorithm was very popular around a decade ago, and then it still remained kind of popular, but there's a lot less research that has gone into this algorithm. And it's incredibly simple to understand, and it is super easy to implement. And it is really, really fast, and it gives great results. Something that you almost never hear in research. So it is absolutely awesome what this algorithm can do, and it's produced some amazing results. The problem is that there's only a limit to how good it can perform, of course. So what is this idea of post-optimization? So in a summary, what it is we are given a covering array. We're given one, and we want to eliminate rows of it. So we try to eliminate, and I'm going to put this in quotes, some notion of redundant rows. And we kind of talked about this before. So I forget if it was homework 1 or homework 2 where you had to build the exhaustive homework 1, where you had to build the exhaustive covering array, and then you deleted all of the rows that where every interaction in them was covered somewhere else. So this row is completely useless to us. And I think I mentioned that the order in which you process the rows actually matters. So if you process them in lexicographic order, that'll be different than if you process them in a random order. Because the time when you encounter the first uncovered interaction will be different depending on how you order the rows. So post-optimization exploits this by trying to put a really bad row at the bottom of the covering array and then put the remaining rows on top so that everything is covered before that last row is reached. Whereas if that last bad row was somewhere else, it might actually be necessary. So it reorders the rows and tries to eliminate redundant ones. So this is the idea. So we're going to reorder rows and keep the last one in place. So the last row is the one we're trying to remove. We actually may remove other ones, but the last one's the one we're trying to remove. Then we're going to locate don't care positions. So who remembers what a don't care position is?
Position that that doesn't really, not really contingent on whatever value is placed there because it doesn't change the interactions in it.
Right. So it's a position that can be changed to anything, and the array is still a covering array. If you keep everything else fixed and you change this position, then the array is still a covering array. So that's a don't care position. So if a row has only don't cares, then we can obviously delete it. And that's something that you saw in homework 1, where if you had a row of all stars, which is a row that has all don't care positions, because no interaction, every interaction's been covered somewhere else, then we can delete that row because it's completely useless to us. So if there is no such row that has only don't cares, then every row must have something that is not a don't care. So for example, if we have like a don't care here, don't care 0, 1, 0, don't care 1, 0, 0, 1, don't care, don't care. So we may be in a situation like this, maybe fewer or more, but every row has some value that's fixed, that's required to be that value. And I think that's true here. Okay. So what we're going to do is we're going to nominate a special row. You can pick any row you want. It doesn't have to be the last one. It could be any one you want. Because we're actually going to run this method over and over and over. So you can nominate a special row, one with either the most don't cares or just pick a random one. It honestly doesn't matter. And then what you're going to do is wherever it is, you put it last in the array. So for this particular row, the one that I picked here, I'm going to move it down to there and then consolidate it like this. So I'm going to move a row down. The one that I pick, I'm going to move it to be the last one. And we're going to go through an example to see how it actually works. And yeah, so then we're going to fill, so this is actually the crucial bit right here. We're going to fill all the other don't cares using the elements of this row. So what do I mean by that? So notice that this is the row that we nominated right here. So what are the positions in this row that are not don't cares? Yeah, the first column, the third one, and the fourth. Yep. So what we do is say, look in the first column. Say there's a 0 in that last row. We scan upward, and if we ever see a don't care, change it to a 0. So say the first row, well, this entry right here is a don't care. So what we're going to do is we're going to fix it to be 0. So what we're trying to do is we're trying to emulate that last row in every other row, if we can. So then the second column in the last row is a don't care, so we don't touch it. The third position is a 1. Well, in the second row, there's a don't care. So what are we going to change it to? We're going to change it to a 1. Yep. So we're going to change it to a 1. The first row in that position has a 0, which is not a don't care, so we don't change it. Then we have a 0 in the last position of the last row, which means we change this one to a 0. And notice that we have some other don't cares in this array, namely in the first row. We just pick a random entry for that because we weren't able to emulate the last row in that position. So let's just say I just changed that to a 1 as an example. And what we do is we then reevaluate the array based on what we just did here and see if that last row is redundant. So if that row has complete don't cares in it, then we eliminate that row. And now we have one fewer row. Isn't that pretty cool? And all you do is just repeat that same method over and over until you think it's too slow. That's it. All you're doing is you're reordering the rows and then just trying to emulate one row everywhere else and then try to eliminate that last row. That's all you're doing here. So there's no real thought into which row you pick in terms of how you evaluate the other entries, the ones that remained a don't care after you fix them from the last row. It's just completely random. There's no thought into this. Yeah.
Just repeat like how you know if you can delete the bottom row.
Right. So what we do at this point right here is we evaluate whether or not the last row has all don't cares or not. So if it does have all don't cares, then we can, of course, delete it. But if it doesn't, if it has some positions that are not don't cares, then I can't remove it. And then we repeat the method with some other row, or maybe we keep that last row there and reorder the other rows. So there's a lot you can do here. But yeah, we just reevaluate the don't care positions, and we just see whether or not the last row is all don't cares. If it is, delete the row. If not, then do maybe a different ordering or something. Cool. Any other questions about the basic idea behind it? Okay, so let's actually go through an example. So I claim, and we're going to just assume this, although you should check, is that the array on the left is a covering array on, how many rows is that? 10? 10 rows, strength 2, 5 columns, 2 symbols. I'm not sure what the minimum number of rows for that is. I think it's 5, but I'm not sure. So I claim that the thing on the left has 10 rows, strength 2, 5 columns, and 2 symbols, which is pretty easy. And I claim that the array on the right has stars equal the don't care positions. So those are the ones that if you keep the rest of the array exactly the same, then the array is still a covering array. So what do you notice about the array on the right? Anything interesting about that array on the right?
I guess you can just delete a row because it's all don't cares.
Yeah, it has a row of all don't cares, exactly. So we can just delete that row. Pretty simple. Okay, so then we just delete that row, which is what we do here. But notice that we can do something else. So we do delete this row right here. So this row is gone. But notice something else interesting. Notice that the array on the right here has 2 rows gone. The one that we deleted, but another row that's deleted. What happened?
Do you merge the first and last rows?
Yeah. So what you do is, so which one was merged? Yeah. So look at this row down here and the first row. What do you notice about those two rows? Yeah.
If you basically smush the text values together, you can end up with a properly sized row, and then you end up with that, and then you end up with a whole row of don't cares, which you can.
Exactly. So because the two rows have don't care positions with no we don't really care about no intersection, but the union of the positions that are don't cares is the entire set of columns. So then we can merge the two rows, and now we have a redundant row. So what we're doing here is we are going to fix the first row to be 1, 1, 0, namely the positions that are down here. So we're trying to we're smushing or merging the rows together. And because of that, every interaction that involves the last row is completely redundant because it appears in the first row. So we can now eliminate that row. So this is not required for post-optimization. This is just another thing that you could do on top of it, which could increase the performance. But notice that don't cares are actually quite powerful in that if you can have this disjoint set of don't care positions like this that involve all columns, then you can delete a row like this, which I think is pretty nice. So then we obtain this array on the right, which is just deleting that third to last row and then the last row. Any questions on how we got that? So now let's actually do start of the post optimization. So what do you see between these two arrays? What is the difference between them? Well, notice the things that I circled. What's the difference? Yeah, the randomly assigned. So it may look like there's some deterministic algorithm like 0, 1, 0, 1. This is just one particular choice that could be made for what can be assigned there, but it's just completely random. Okay, so then let's look at this. So we randomly assign, so we have this array on the left now. Now what we do is we do the same thing again. We evaluate the don't care positions again and just see what happens. And what do we see now? Get a row of all don't cares. So then we can delete that row. And we have this array on the left. And what else can we do? So we eliminated that row. Oh, so notice something interesting here. So this row's gone, obviously. But what do you notice down here? So this is not required for post-optimization either. But what else do we see? We're again merging. So what do we do now? Well, let's see. What can we do? So what we can do is we put the 0 down here. So notice that the 0 in this position right here, there's a don't care way down at the bottom. So we just replace it with 0. And in the same row at the bottom, we have the other position, which is a 1, also being a 1 downstairs. So any interaction in that, fifth row, which involves the second column and the fifth one, is now covered by the last one. And so now this row is completely redundant. Pretty interesting. So from this really simple algorithm, we can get a dramatic reduction in the rows. And it's actually pretty amazing, and we're going to be reading about this on Wednesday and Friday because it's a different application. On Wednesday, we'll see how big of a reduction that this can actually get. With like 1 minute of computation, you can eliminate thousands of rows in a covering array produced by any of the methods we talked about in class so far. So, such as the random method or the density method. Any one of those algorithms you can apply post-optimization to and get dramatic results out of that. So for a class project, one thing that you can look at is, well, what is the right thing that we need to do? What are the right rows to select? Should we really do a random selection, or is there a particular way of selecting them? Because if you think about the density algorithm, it tries to cover a lot at the beginning, but it leaves a few interactions at the bottom. Should we pick the ones at the bottom, or should we pick the ones at the top? I'm not really sure what the answer to that is. If we reorder the rows, well, that might screw up what the density algorithm is known for being greedy. So I'm not sure what the best idea is. So that would be a really good project to do. Any questions on the example itself? Okay, so let's bash ATeach some more. So I mentioned that ATeach had claimed that this particular parameter set had like an unbelievable result, which is the 180 here. And it turns out that there's an online implementation that you can download that it doesn't quite achieve that, but it's relatively good. 198 rows versus they claim 180 by the authors, and there's obviously a disparity between the two. There's some work by Calvagna, I can't really pronounce that, and Gargantini, which look at a bunch of different methods, see what happens, and none of them can get close to 180. So we haven't talked about simulated annealing, but it's another randomized algorithm that we will talk about. And it does a little bit better, it gets 183. Then there's a mathematical method by Marr and Stevens. So you may think that's meager. It's Marr, believe it or not. So Marr and Stevens do better than that. Another method gets better, and it can be reduced even more. But post-optimization is currently, as far as I know, the best algorithmic method for this parameter set today, even though it's a decade later after the paper was published. But it turns out that this is not the best known size, and turns out we can even do even better than that. So, of course, this is not obviously the end of the story for this parameter set or any parameter set, but this is just something that you should think about, that such a really simple algorithm, you don't have to really think that hard about the algorithm to understand how it works, but it's extremely powerful against all of these other algorithms, against ATeach, against conditional expectation, versus the random method, versus any method that anyone's implemented. This one is the best in terms of starting off with a covering array and then trying to reduce its size, which is actually quite amazing. So this is really something to look into. Okay, any questions about post-optimization? Yeah.
What's like the runtime? Like how long does it take?
So that's actually a really good question. It depends on your tolerance. So if you look at the top here, you basically just keep going until you think it becomes too slow. Because what you can do is you can just try different orderings of the rows for as long as you possibly want and never find an improvement. So that actually does happen. So you may want to set like a time limit of like 3 minutes per improvement or something. And then once the time limit is reached, then you just stop at that point. Yeah. So that's something to look into also. Does the time limit actually really make a difference here? Or can we just set it to be like 1 minute and it'll just be as good as if we set it to an hour? So that might be something to look into too. But yeah, it's really based on your tolerance for how slow you want it to be. Any other questions about post-optimization? Cool. I'll see you on Wednesday. Remember, there's a paper on Wednesday.